Hi everyone. This topic has been on my list of to-do things for a very long time. Here is my attempt at trying to explain the problem and some of the solutions. In their white paper, ABI Research estimated that the total worldwide overall energy footprint of cellular technology reached roughly 19.8 million tons oil equivalent per year in 2020. This is expected to grow to 51.3 mto in 2030 with a compound annual growth rate of 10%. This would be equivalent to the total energy consumption of Sweden or Norway, or roughly the same amount consumed by all the households in Australia or the United Kingdom in 2030. This is a huge number. You can see the breakdown on the chart. The GSMAI white paper provides some good breakdowns on what and where the energy consumption happens. This figure, for example, shows that 23% of the network OPEX is spent on energy. This chart shows energy consumption based on the technology. While the majority of power is consumed by LTE, there is still a huge amount of power consumed by the legacy networks. As 2G and 3G networks are shut down, the power consumed by those networks will reduce. Similarly, as more 5G networks are rolled out, the power consumption in 5G networks will increase. This picture explains where the power is consumed. As you might have guessed, most of the power is consumed by the BBU and RRU. It also depends on the architecture. We are taking the simple case of distributed RAN or DRAN. Centralized and Cloud RAN assumptions would be slightly different. In case you do not know what DRAN and CRAN is, we would recommend watching our tutorial on different types of RAN architecture. In their white paper and presentations, Huawei explains the way they see the breakdown with regards to energy usage. For example, roughly over 50% of all the energy consumption is in the RAN. Also, RAN energy consumption is 25% of the RAN OPEX. Let us now say that we want to see how an ideal network would behave and how a real one behaves. In an ideal network, the power is only consumed when there is load. So for example, if there are no UEs that are actually using the network, the power consumption would be zero. While if the maximum number of devices are using the network, then the power consumption would be 100%. In the real network, there is always a minimum amount of power consumption, which we can refer to as the static part, while the power consumption changes based on the load that we can call as the dynamic part. For energy saving within the network, we want to reduce the static power consumption so that it matches the ideal scenario. As far as RAN energy savings are concerned, we can say that there are roughly three layers of RAN energy savings. The first is at the network level, where SON or self-organizing network algorithms along with energy optimization policies and AI/ML based policies have a role to play. The second is at the site level, where optimization at site level can be applied based on the site load, etc. Finally, we also have the equipment level energy optimization. Here it's generally more efficient equipment including servers and remote radio heads that can reduce the power consumption. When we talk about RAN energy saving, generally there is a trade-off between the scenario, the time for which energy saving can be applied, and the features that can be used. Let us look at some of these to try and understand how energy saving can work in the RAN. We often talk about multiple generations and multiple layers in each of these generations. While during busy hours, each of these may be required, during off-peak hours, some of these layers could be switched off to save the amount of power consumed. These have to be planned carefully as it would depend on each site when it becomes less busy, how does a network hand over the devices to other layers, etc. In the end, the network has to ensure that the quality of experience is not affected. ZT Communications magazine in March 2021 looked at energy consumption challenges and prospects on B5G communication systems. One of the articles on enabling energy efficiency in 5G network looks at 5G NR cell switching on-off schemes in 3GPP to achieve energy efficiency in 5G RAN, including intra-system and inter-system energy saving schemes. We recommend having a look at the article as it covers quite a few details. You can find the link in the references section of the slides, which you can download from our SlideShare channel. In 4G and 5G, we can take power saving one step further by switching off the power amplifiers when there are no UEs scheduled for transmission at that time. In their recent article, Ericsson explains that these short gaps are utilized to reduce power consumption in the network by quickly putting components into sleep mode and then activating them again before the next transmission occurs. The longer these time gaps are, the more components can be put into sleep, and the lower the energy consumption becomes. A feature that utilizes these time gaps is known as micro sleep transmission, which puts radio units in sleep mode whenever there is a time gap. In the 4G standard, these time gaps where micro sleep transmission and other energy saving features can operate are always very short, at the most 0.2 millisecond. This is because the 4G LTE standard mandates that a large amount of synchronization signals, reference signals, and system information should always be transmitted over the entire bandwidth. These signals are needed to secure cell coverage and a good connection with users. But they also limit possible energy savings we can achieve with LTE. The 5G NR standard has been designed based on the knowledge of typical traffic activity in radio networks and the need to support sleep states in radio network equipment. Therefore, 5G NR provides much better support for implementing energy saving features in network products. In 5G NR, the time between mandatory transmissions can be as long as 20 milliseconds in standalone mode and 160 milliseconds in non-standalone mode. That's 100 to 800 times longer than the corresponding value of 0.2 millisecond for LTE. In addition, 5G NR requires far less always-on signaling transmissions in the frequency domain. This is often referred to as ultra-lean design of the 5G NR physical layer. Since 5G NR has significantly fewer always-on signals, the technique of shutting down the power amplifiers during microsleep transmission provides much larger savings in low and medium traffic scenarios compared to LTE. Although the use of microsleep transmission in LTE provides impressive energy savings, this works even better for NR. The power consumption reduction for using microsleep transmission during idle mode in LTE is approximately 45%, while for NR, an even more impressive energy consumption reduction of 70% is achieved. Finally, this slide from Huawei presentation shows examples of how intelligent scheduling can create opportunities for shutdown of the power amplifier, thereby allowing opportunities for saving energy in the RAN. The examples shown here illustrate intra-carrier scheduling alignment, inter-carrier scheduling alignment, and LTE and NR coordinated energy savings. Here are the references that you can get in the slides. Hopefully, this short presentation provided an idea on how 5G energy savings can be done. Some of these savings are in the hardware infrastructure, some of them in the software, like the scheduler, which is a proprietary implementation by each vendor and often the differentiator. Also, the 3GPP standards are defining some approaches that the vendors can implement in their solutions. Thanks for watching and see you again soon. Goodbye.